All right, welcome back. Yesterday we learned about the tangent slope, how to find a slope using only one point, which was new. And what we're going to find today is that that's a very useful skill because it can also allow you to find the instantaneous speed of an object. So that's not like the speed over a certain amount of time, but the speed at an exact instant. Um, Here are a whole bunch of things that kind of look alike. Here's what we're talking about today. This would be something that I think you would find on page 22 at the top, the instantaneous or exact rate of change, and it should look really familiar. It should look like, hey, limit as h goes to zero of the only difference is it looks like this t is not what we were using yesterday. I think yesterday we were using an a, and the reason is because we're talking about rates of change, which are almost always going to be based on the change in time, whether it's miles per hour or gallons per minute or whatever. I mean, we're almost always basing things over time, and so we use t to represent time. Other than that, it's the same. I mean, here's your tangent slope from yesterday, right? Versus what we just talked about right there. The only difference is the variable we chose to use, which isn't that big of a deal. Okay, in calculus, you're going to call it the first derivative, and the nickname is f prime. You put a little tick mark next to f. That means the first derivative of the function f. And look what it looks like. This is the definition of the derivative. What? It's the same thing. So when I'm telling you that you've now learned calculus, I'm really not just making that up. I mean, this is the initial progression into calculus. You've now learned the definition of the derivative of a function. It's really just the difference quotient as the h value, the distance between points goes to zero. Same thing. Same thing, different name, slightly different meaning. But our focus today is definitely going to be this one because we want to solve some application problems. Um, these are a bunch of things that I want you to understand are synonymous. Okay, now that we have this little formula here, first of all, we could say the slope of the function y equals f of x at x equals a. I mean, we've talked about slopes of lines since algebra 1, but we've never really talked about the slope of a parabola or the slope of a square root function because it's always changing along the function. It's speeding up, it's slowing down. It doesn't have just one slope all the way through like a linear function does, right? Well, now that we know how to find tangent slopes, we know how to find the slope of a function at a particular point, which leads directly into number 2, the slope of a tangent to y equals f of x at x equals a. See, those things are really the same thing. The slope of the function at a point, the slope of the tangent to the function at the point mean the same thing. Today we're going to tack on number 3, the instantaneous or exact rate of speed, rate of change of the function at that point. It means the same thing. And then, of course, there's our definition, right, of the difference quotient with the limit, which is exactly how we find those things. So that means the same as the first 3. And then with the asterisk, because we're not really going to get into that, like in this textbook, and I don't think you'll use this one next year, but the one we've been working out of, chapter 2 is limits. And this is as far as it takes us, the difference quotient. But chapter 3 immediately starts with differentiation. And I mentioned yesterday that calculus comes down to 2 big ideas, differentiation and integration. And we talked about Pierre Fermat yesterday and how he had this idea of how to use this difference quotient and take the limiting values of those secant lines, and it inspired Isaac Newton and roughly around the same time Leibniz, another mathematician who to really develop calculus and come up with the fundamental theorem of calculus, which is what connects differentiation and integration. So this stuff is all connected. So we're not going to really call these things the derivative, but it really means the same thing as the first four. Um, you can see 5 problems that look like they're asking you different things, but they're really all asking the same thing, which is nice because you can solve them all the same way, but it can also be confusing because you may not recognize them all. I will tell you this: look for words like at, um, at, right, exact, instantaneous. These are all giveaways. Tangent. These are all giveaway words that tell you that we're not just dealing with average rates of change anymore. We're really dealing with something much uh, more powerful. All right, so here's the example that's built into page 22. I rewrote this because I was looking over this. And, I mean, it's been around for years, but I was looking at this the way it was written in your course pack, and I don't even know if it's a complete sentence. It doesn't really make a lot of sense. Um, so I rewrote the problem so that it had some meaning. I mean, it talks about dropping a rock, but we don't know how high we are when we drop this rock, and then it talks about the interval um, and the average rate of speed over that interval, but really it wants to know the speed at t equals 1. So it wasn't very good. So I just changed it a tiny bit to say, okay, yes, the acceleration function is still 16t squared, but this is something you'll learn in physics, and it's the position function where you have to know where you're starting from. That's h. It looks like h0, but it's when you see that little zero, it means initial in like physics or science class. So that means h naught is how you say it, not not naught, but naught naught. So h naught means initial height. V naught would mean initial velocity in a problem. So whenever you see that, that's what that means. And then the reason I'm subtracting the 16t squared is simply because this rock is falling. I mean, if the rock was flying up into the air, we'd have an upward parabola and we'd have a positive t squared. But unfortunately, the rock is falling, and the parabola should be going down, right? Does not make more sense for a falling item. So that's why we subtract it. That's why this formula works, okay? And that was another issue with your notes, is it just used this gravitational acceleration function in place of the position function, so it wasn't entirely accurate. So I did tweak this just a little bit. So today's lecture is very similar to your notes, but just a little different in case you want to get confused. But I was tired of it not making sense and needed to get fixed. So here's how this is going to work. Your work is going to look similar to this, but just a little different. Your work's actually a little simpler because the 16t squared is an easier function to follow than 200 minus 16 t squared. But it is what it is, right? So we were interested in t equals 1 second. And so we're going to go ahead and plug that 1 in for the time, right? Time equals 1 second. And now we're going to find the instantaneous speed of that rock at 1 second. So it's very similar to the math we did yesterday. We used a difference quotient so we can find the exact speed at that point, not an average speed over time. We start off with just some algebra, right? I have to put that 1 plus h into the first function. I have to put 1 into the second function. That's what we do right here. I have to square that binomial 1 plus h. So that's going to be 1 plus 2h plus h squared, right? It's not just 1 plus h squared. Don't do that mistake. Um, the function over here is pretty simple because it's really just 200 minus 16. So that's just going to turn into a 184, and you probably could have done it a little earlier. Meanwhile, I'm distributing the negative 16. Don't forget the negative has to go to each of those 3 terms in the trinomial. They all become negative, right? And finally, I can clean some stuff up. 200 minus 16 in both cases is 184, and this is what I end up with. What we want to happen on all these problems is for the h in the denominator to somehow go away. Most of the time that's because it cancels. And that's exactly what happens after I get rid of those 184s. Everything that doesn't have an H should cancel, right? And then a factor, and there you go. Look at that. The H in the denominator is gone. I can now right here go ahead and make that substitution, evaluate the limit. Notice the limit sign disappears at that point, and I get negative 32. Now, some people, that's going to freak them out because they're like, well, you can't be going with a negative speed. And actually, that's true because speed is the absolute value of velocity. But velocity is a vector that has not just a magnitude, which would be the 32 feet per second, but also a direction. And so the negative actually makes a lot of sense because it's falling. So the velocity at 1 second is negative 32. The speed is the absolute value of velocity. So the speed doesn't care about direction, just how fast it's moving. And so you know, you could turn it into a positive. I've never taken points off for if people keep the negatives or not, because usually these questions just ask you for the speed. If people accidentally leave the negatives in, I don't, because we don't have enough time to really get into the physics. That's for physics class. I really just want you to be able to do the math, but I do want you to try to be as accurate as possible. So these are good things to know about. And that is the example in your course pack. If you notice, what you actually saw was probably this, right? Which was very similar, okay? And we got 32 still, but it wasn't really using the right function. It was just using an acceleration function. So if they asked you for the speed, you would have been right. But if they'd actually asked you for the velocity, you would have been wrong because positive 32 would mean this rock is flying up into the air. All right. I'm just pointing out a couple homework problems you'll be working on tonight, 23 and 27. And notice how they both start with a height. This one starts at a 100-foot tower. This one starts at a 200-meter cliff. And then it gives you this one just gives you the function right out. Okay. But this one, gives you the free fall equation, the gravitational equation, and you have to put those together. So you would have to know that that's going to be 200. Okay, maybe that won't work. Let's try this instead. You'd have to know that's going to be 200 minus 1.86 t squared for your function. Okay. I think 27, 28 are very similar, but those are just a couple problems you'll be working on this evening. So here's what I'm going to do. 25 and 29 are like in your course pack. It's part of the assignments. 24 and 28 were not. So I'm just switching two in and switching two out. So it actually helps you because I'm going to give you two more examples than you would normally have. We've never done these as examples before. But then the homework itself doesn't grow, it just stays the same. We're just replacing two problems with two problems. So we're taking 25 and 29, turning them into examples for you. We are adding 24 and 28 into the homework just to make sure you're getting 6 practice problems, which I think is enough. So this one's different. This is why I wanted to do this one. It's talking about the rate of change of the area of a circle with respect to the radius. And see, here's the deal. You have a circle and starts off with a tiny radius and probably a pretty small area. Now as it grows, right, as that circle grows, I think I'm going to start with a new circle. This one's annoying me. There we go. All right. So as the circle grows, obviously the radius is getting longer, but the area is growing faster than the radius. And here's why. The radius is just a line segment. It's one-dimensional. The area is two-dimensional, so it's growing in two different dimensions. So it's actually growing at a faster rate than the radius is. You kind of learned this in geometry when we did LAV problems, length, area, volume, and we were setting up ratios. Like if the ratios of the sides were A to B, the ratio of the areas would have to be A squared to B squared, right? And it's the same idea. So this wants to know, exactly how fast is the area growing when the circle gets to 3 inches. I don't really know that's a 3-inch radius, but that's basically what it's asking. Okay, so it's a little confusing because they don't give you a formula or anything, so a lot of people get confused, which is why I kind of wanted to do this as an example. But we know the area of a circle. The area of a circle is pi r squared. So you do have a formula. And what I'm going to do is I'm going to turn this into a function. I'll call it a of r, I guess, a of r. The area function is pi r squared in terms of the radius, so the area in terms of radius. And we're going to do, to find this, this change, the exact change at 3 inches, we're going to do the limit as h. H isn't going to change no matter what. I mean, we could be talking about time or random a values or radii, it doesn't matter. H is the distance between the x values, or in this case, I guess it would be the r values. That's not going to change, okay? And we'll do a of, now remember, they want us to do 3. So I'm going to plug a 3 in for r plus h minus a of 3, and we'll put that all over h. So that's really what we're doing. It's the same idea. And you don't have to call this a if it confuses you. You can call it f of a still, or f of r, whatever you want. But it's really the same stuff. Now, specifically, the function is pi r squared. So it's going to be pi 3 plus h squared minus pi 3 squared over h, right? Which is going to be the limit as h goes to 0 of, let's do some algebra. Remember, it's not 9 plus h squared, please. It's 9 plus 3 plus 3 is 6h plus h squared minus pi 9. And I tell you what I'm going to do here. You could distribute this pi, and you would get a 9 pi and a negative 9 pi, and they would cancel, and things would work out the same. But it actually saves you, if you have common constants, it's going to save you so much time if you just pull those constants out front. Okay, I just pull that out. Now, technically, it's limit as h goes to 0 of pi, but we know that the limit of a constant is itself. So now all I have to worry about in here are just these pieces. Oops, this pi got factored out. This is just the normal kind of algebra pieces, and we do see that the 9s are going to cancel, and I can now factor out a h from the 6 and the h squared. So they cancel, which means that I'm really just taking the limit as h goes to 0 of 6 plus h. Don't forget, you have to show the substitution of this, right? So you have to show the 6 plus 0. Notice as soon as I make my substitution, that's called the evaluation step, I don't have to write the limit anymore. So I just get 6 pi. And this would be like 6 pi square, I think it's in feet. Is it feet or inches? Was inches. Okay, so 6 pi square inches per inch of radius would kind of be what the rate is. So exactly at a radius of 3, the area is changing by 6 pi square inches per inch of radius. And then the bigger it gets, the faster the area is going to grow. But it's not a it's not a one-to-one thing. It's not growing by 3 inches at, by 3 square inches at 3 inches. It's by 6. And the problem that you're going to see in your homework is going to be 26, and it's the volume of a sphere. I really should just make you look this up because it would only take you 10 seconds on your phone. But I'll go ahead and give it to you. The volume of a sphere is 4/3 pi r cubed. So as a hint, 4/3 and pi, these are constants, and so kind of like we factored out the pi in the previous problem, I would not start multiplying things by 4/3 pi because that's going to make things look a lot uglier. Once you get your limits set up, I would factor the 4/3 pi's out and leave them out there until the end of the problem, and just deal. You're going to have fun enough with an r, the 2 plus h being cubed, which is going to take a little bit more work algebraically to do 26. So don't worry about that 4/3 pi, but that's the formula you would use. That's the volume of a sphere. So we would call it, v of r, v or of x, or whatever you want to call it, and do the work with that. Okay. All right. The last example I'm going to do for you here is 29. It's a horizontal tangent problem. Number 30 is just like it, and I like to have people do this without without kind of going through stuff and just see what they come up with. But since we are doing remote learning, I'm going to go ahead and go into this a little bit more. This is just a function right here. All right, and whatever strange old polynomial random function. I just want to show you that, as you go through this polynomial, look at all I mean, it has infinitely many points, and each of those points has its own tangent, and so it has infinitely many tangent slopes. Look at all these tangent slopes. Okay, look at all these tangent slopes. See, now it's decreasing. Now those tangent slopes are negative. In general, what you're going to find is you're going to find that tangent slopes are positive when the function is increasing and negative when the function is decreasing. But you just see all of these different tangent slopes based on how fast or how slow the function is changing at a particular point in time. And I think that's probably enough to give you the idea of what's happening. Now, this is looking for where your tangents are horizontal. So let's look for tangents that look like they're horizontal, like maybe this one, maybe this one, maybe this one, right? So I'm going to go ahead and I'm just going to call those points out. That's a point of tangent C. That's a point of tangent C. That's a point of tangent C for for those horizontal tangents. And then I'm gonna freeze those points for a second, and I'm gonna make everything else go away to clean this up. Boom. What do you notice is left? I mean, what do we have left now that we just look at these points? If you're thinking to yourself, wow, Jacek, it looks like those points are always happening either at local maximums, there'd be another one here if we would have kept going, or local minimums. There would have been another one here and another one here if we would have kept going. You're absolutely right if you notice that. If you didn't notice that, then I guess maybe I should have given you more time. But here's the thing. If the function's increasing, the tangent slopes are positive. If the function is decreasing, the tangent slopes are negative, right? Well, if a function is increasing and turns into decreasing, it has to hit that local maximum, that peak, right, before it starts going back downhill. Well, that's when the tangent is going to go from having a positive slope to having a negative slope. And we all know that on the number line, the number between positive and negative numbers is 0. Now, as the function has negative slopes, okay, and it wants to go back to having positive slopes, it's going to have to transition once again from negatives to positive. It's going to have to go through 0 again. So basically, anywhere that a function has a horizontal tangent, it's going to have a local min or a local max. Okay, kind of cool. This is something you'll definitely talk more about in calculus. This kind of stuff that you explore. Now, this function is a little bit simpler than that crazy one I just drew. It's just a good old-fashioned parabola. Looks like a positive parabola. And so what we know about parabolas is they only change direction once, right? And so wherever the vertex is, that's got to be the only place where the horizontal, you have the tangent that is horizontal. Okay. If it was in vertex form, or if it was a really simple one, I would already know where the hell it is, but I don't. So I guess you could use completing the square and put it into HK form like you did in algebra 2. and then you would know where the vertex is, and that would have to be the x value where it's horizontally tangent, and then you could use that method to try to find the location, okay? But since we're trying to learn how to use the difference quotient, I'm going to teach you how to do one of these problems. And it's far more powerful than the other problems we've been doing, far more powerful. But the algebra is a little bit nastier. Not a ton nastier, but there's just more variables and less constants, and so that makes it a little more laborsome. Let me show you what I mean. We have f of let's call it, you want to use a or you want to use x? I mean, a is what we're supposed to be using because that's kind of what's part of the difference quotient. That's kind of the definition of the tangent line that's in your notes. I usually use x plus h. That's actually the derivative. So it means something slightly different, but it really works the same. I'm going to go ahead and use that just because I'm more used to it, and it's not a big deal. You could use a, it would be fine. But this is what f of x plus h would be. And see, here's the problem. I don't know what x is. On all the other problems I've known, like, oh, they want me to find the tangent at x equals 1, or at x equals -2, or, oh, they want me to find the speed of this at time equals 1 second, or the radius at, r equals 3 inches. They've always given me that value. And here they don't. Here I'm trying to find that value when we get a particular or very specific tangent slope. So I'm going to leave it as a variable. And this is what I mean. The algebra is a little more intensive. So I'm going to go ahead and do x plus h squared plus 4 times x plus h minus 1. And so we're going to FOIL that out. X squared plus x times h, x plus 8 times h, so 2xh plus h squared. So that's that squared, and then distribute the 4, so 4x plus 4h. By the way, one of the most common mistakes isn't the squaring. It's people get so relaxed after they get done with the squaring, they forget to plug the x plus h into the 4x, and they just get 4x instead of 4 times x plus h. So be careful about that. And then, yeah, I think that's about it. I don't know if I really see any common terms, so maybe we just leave it like that. So what is, f of x? Well, f of x is just what we see, right? X squared plus 4x minus 1. If you use a plus h and f of a instead of x, well, turn all these x's into a's and it's the same thing. But now we can go ahead and use our tangent slope formula. Limit as h goes to 0, always h, right? Of f of x plus h minus f of x over h. But we know exactly what these are because I just found them. Some people like to do this work within the difference quotient. I used to do that, but now I think it's just a little cleaner to do it outside. It's really up to you. So here we go. X squared plus 2xh plus h squared plus 4x plus 4h minus 1. That whole chunk of stuff right there, right, was f of x plus h. I'll, just to make it a little more organized, I'll do this guy in red instead, so minus. I'm going to use parentheses because if I don't, I'm going to forget to distribute that minus sign. I have to have those parentheses. Very, very important. Okay. So that's f of x. So f of x plus h minus f of x is, you ready? X squared plus 2xh plus h squared plus 4x plus 4h minus 1 minus x squared minus 4x plus 1. Once again, remember, you got to distribute that minus sign through there. This is all over h, which is really the only problem we have is that h down there because it can't have a 0 down there, right? All right, so you can see that the algebra is a little bit uglier for a couple steps, just a couple steps, and then it cleans up. So watch how it cleans up now. Remember, if that h can cancel, it only can have things that have h's up top. So like x squared doesn't have an h, but look, negative x squared. 2xh has an h. It doesn't look like an h because it's kind of sloppy, but H squared has an H. 4x doesn't have an H, but don't worry because there's a negative 4x. Negative 1 doesn't have an H, but don't worry because there is a positive 1, right? And so soon enough, it cleans up to 2xh plus h squared plus 4h. That's all that's left is these three pieces, which they all have an h. So why don't we factor that h out? And then cancel it. Okay. Now, here's where I told you this is way, way more powerful. Okay. When I go ahead to evaluate this limit, I want you to realize I'm not going to get just a nice specific value. There's only one h left, so that's where the 4 goes. What I get is 2x plus 4. In calculus, you will call that, f prime, the first derivative. It's a formula. It's a formula, not a um, not a just a specific slope, but it's a formula that will give you the slope at any x value. That's the power of that. So we don't really need to use this right now. All we really need to do is set it equal to what kind of a slope does a horizontal line have again? Oh yeah, 0. And so 2x is equal to negative 4, right? Subtract the 4, x is equal to negative 2. At negative 2 is where we're going to find the horizontal tangent. X equals negative 2. Now, that's not a point. I think this asks for at what point. So we would have to finish the problem off by plugging negative 2 into our function. So I would get 4 plus negative 8 minus 1. So 4 minus 9, I guess, negative 5. That's the point. So back 2, down 5. That's where the vertex of your function is. That's where the tangent will be horizontal. Okay. Now I'll show you a little magic here on the graphing calculator. Let me pop it open. That was not the graphing calculator. Here we go. All right, I open up the graphing calculator and I put our function in, x squared plus 4x minus 1, and you can see, sure enough, it does look like the vertex is negative 2 down 5 right here, right? But let's watch that horizontal tangent. Remember, a horizontal line is just y equals whatever, right? So let's go ahead and plug in another another function, and let's make that function negative 5, since that's the height of the vertex, right? Boom! Look at that. We just found the tangent to this function at the vertex, and sure enough, it is a horizontal line because those tangents are going from negative slope tangents to positive slope tangents. But let me show you how powerful that function is. Let's pick another x value in here. Here's 0 maybe. So 0 looks like 0, negative 1 is the point there. But let's go back and do just a tiny bit of math. And I'm just showing you how powerful this formula that you found is. Okay. So let's switch to another color. So let's say I'm interested in the tangent line at x equals 0. So normally I have to plug a 0 in for a and do the difference quotient and get the slope. And then I can use that slope to find the equation of the line. Well, check this out. I've got this powerful formula right here, 2x plus 4, that finds the tangent at any value. So if I put a 0 in, I'll call it m, right, for slope. If I put a 0 in for x, it's going to tell me that the slope of the tangent line at that point we found at 0, and it would be, by the way, 0. I think we thought it was 0, negative 1. It would be, because if I put a 0 in here and a 0 in here, all that's left is negative 1. So the slope of the tangent line at 0, negative 1 is 4. Now if we do y equals mx plus b, and put the slope of 4 in with a 0 and a -1. And this is kind of silly because that -1 was on the y-intercept, so we kind of already know that the y-intercept is going to be -1. But if we do y equals 4x minus 1, it should be tangent to our graph at exactly that point that we just kind of randomly decided to pick. Okay, so let's go back into here, the graphing calculator, and we're going to enter that function right in there. Okay, let me move this out of the way. We're going to do, what was it, 4x minus 1. And go ahead and graph that. And, oh, look at that. It is tangent right through that point. Kind of hard to see. Maybe if we zoomed in a little so it wasn't so steep, you could see that it really does just hit a single point. So let's go from maybe like negative, let's go from like -1 maybe over to like 3, no, to 1. Yeah, that's a good real skinny narrow area. And you can see that that line really is just hitting that 1 point right there. Okay, pretty cool. And that's the power of derivatives, and that's what this formula that you've been learning is going to allow you to do, except there's a lot of other types of functions, and you're going to have to learn a lot of tricks, but you're also going to learn a lot of shortcuts, and that's going to be the cool part, to really fun, see how easy some of this stuff is. For example, the power rule could do what we just did down here. Okay, it would find this dude for you right here. It took us like what, about 3 or 4 minutes. It could do it in literally, okay, I don't want to understate this, like 10 seconds. Um, because you're my close personal friends, I'll show you what I'm talking about. Okay, if f of x is x squared plus 4x minus 1, the power rule says multiply the exponent by the coefficient and then drop the exponent down 1. So f prime becomes 2 times 1 times x to the not squared anymore, but first power, so we won't write it, right? And remember, this is like a 1 here, so that would be 1 times 4 is just 4, and then the x drops down to a 0. Well, x to the 0 is just 1. And then this is really like 1 times x to the 0, because the x isn't there, but 0 times 1 is 0, so you lose the constant, and look what you got. What? It's like magic. Um, so, um, unfortunately, the work you have to show on your problems, whether it's homework or quiz questions, are going to have to show the work. In fact, we're not going to have a quiz this week, because we're going to keep practicing the stuff all week. But probably early next week, you're going to have a quiz. And I'm serious, it's probably going to be 2 questions. It's going to be really short, but you're going to have to show um, the difference quotient. You can probably check yourself with this little shortcut, because it is pretty cool, but you're going to have to show the work to get the credit. So anyway, hopefully these examples were helpful. Um, Notice how I made a couple little changes. I added 24 and 20, so this is back in, that wasn't in there before. 28's back in, but notice I took out 29 because it was an example, and I took out 25. So 2 came out because we just did them, 2 went in. So it's 6 application problems plus 2 problems, kind of like you were doing on 15 and 16 last night. By the way, 18 is going to be really confusing for you unless you remember there's 2 things that have to happen for a tangent line to exist. And the one that takes a lot of time to check is that the tangent slopes from the left and the right agree. But there's one before that that's much easier to check. And if you use that on number 18, it actually makes 18 the fastest problem of that little set of 4 problems, 15 through 18. So hopefully that helps speed that up. And good luck on your application problems. And remember, couple help sessions tomorrow to try to really help people understand this stuff, since, after all, it is calculus. Have a good one.